Consider the Internet, the metaverse. The information flows are carried by the global fiber optic web. The hubs of Internet information are large data centers where the information come, processed, computed, and flow out. Behind the large racks of servers are optical fiber terminals, via which, data in the form of light signals come and go in colorful noodle-like strands in the pictures. A close-up shows the basic unit enabling this data come and go. It is a package of a pair of devices labeled as TX/RX, which are abbreviations for transmitter and receiver, respectively. Their functions are to convert data in the form of voltage signals to light signals and vice versa. Most often, they are packed together in one unit, known as the transceiver, equivalent with the transponder in RF and microwave communications. Why is there a need for conversion between voltages and light waves? The reason, as discussed in Part 1, is that the higher the data rate is, the higher is the electromagnetic wave frequency required to carry that volume of data. Given a data rate, the electromagnetic carrier frequencies have to be a large multiple of it, such as 10 times, 100 times, or several hundred times higher. Hence, consider wireless data communications as an example. The electromagnetic carrier waves have been shifted steadily into higher frequency ranges to meet increasing demands. As the computing power of a data center increases, so is the demand for data rates. 1 gigabit Ethernet was once considered ultra-fast, then 10 gigabits, and now it is several hundred gigabits and increasing. Another requirement besides the frequency is that the electromagnetic waves must be transmissible with little loss in the conducting media. Hence, for hundreds of gigabits per second, light waves of the frequency range of several hundred terahertz in low-loss optical fibers are presently the best technological solution to this demand. Inside an optical transceiver are two essential optoelectronic devices. One is the laser diode transmitter, which gives light waves encoded with data. The other is the optical receiver, which detects the incoming light waves. It usually consists of a PIN photodiode and an integrated transimpedance amplifier. This is the reason for this Part B of Lab 4, that is, to study the circuit properties of a transimpedance amplifier. This is a generic schematic of a typical optical receiver. For the Internet, the most advanced optoelectronic and solid-state device technologies are required to meet the demands of the high data rates. In this Part B of Lab Assignment 4, we use a far simpler and much lower tech. However, the optical receiver circuit that you will build has all the essential features for one to learn the fundamental concepts of this technology. The transimpedance amplifier to be built for Part B and Part C is quite similar to the voltage amplifier built for Part A. Then both are connected together to form an optical receiver. The previous discussion is an introduction to the broad concept of optical receiver. Here we will discuss in details about the learnings and lab work of Parts B and C. The communication device that we will test with the receiver in this lab will be the humble household remote control, which is an optical transmitter, using infrared in the wavelength range similar to short-reach multi-gigabits transceiver connecting the servers in a data center. The difference is that the data rate is a billion times slower. Nevertheless, one can learn some basic concepts about modulation and signaling with such a simple device. The remote control sends a message to the appliance using an infrared light beam. It uses a LED transmitter. The message is received by an optical receiver, ubiquitous in all entertainment electronics, which includes all the subcomponents integrated in a highly compact, inexpensive package. What to be built in Part B is equivalent to this device, and the circuit will be used to detect the remote control signal amplitude modulation, which is usually around 40 kHz or so. At the most basic level, a learning objective is to study the op-amp as a current-dependent source, as opposed to the voltage-dependent source in Part A. The negative feedback here is to control the voltage output from the input current. The photodiode acts like a current source, where the current magnitude is proportional to the incident light power. With the approximation of infinite open-loop gain, X inverting voltage can be set as 0. Then, Kirchhoff's current law yields a relationship between the output voltage Vout versus photodiode current I1. The result is that it is a current voltage conversion. However, as discussed in Part A, how it works is not the most relevant and important. There are thousands of op-amp products to choose, with a wide price range. What make them different from each other are the applications that each is designed, optimized for, and which determines the relative merits of various op-amp performance features. We have learned in Part A properties such as saturation, frequency response, and gain bandwidth, slew rate. These are abstract concepts in pure circuit theory, but they are relevant and meaningful in the context of applications, which is the reason for this Part B and Part C. For example, what is the implication of the gain bandwidth limit? We will see that it determines the data rate in communications, as will be seen later. The light sensor we have is known as a photodiode. A photodiode is the opposite of a LED. A LED takes a current and converts its electrical energy into light that it emits. The photodiode works by the reverse process. It absorbs light and converts the light energy into a current. A cousin of the photodiode is the photovoltaic cell, or more popularly known as the solar panel, which takes sunlight, and converts its energy into a current power source. The photodiode is the most prevalent and popular sensors. Behind every cell phone camera lens is a sensor array, what is equivalent to the retina in our eyes. An array sensor has millions of pixels. Each pixel may have up to 3 photodiodes for the 3 primary colors, red, green, blue. The current from a photodiode needs a transimpedance amplifier to convert it into a voltage. There are 2 common approaches, one is the resistive transimpedance amplifier, and the other is the capacitive transimpedance amplifier. We have seen the use of a capacitor to store electricity in Lab 2, and we will learn more about using the capacitor to integrate a current in Lab 5. This integration capability is applied to common camera sensor arrays, since an image for the human eye is an integration of light over the retina slow response time. For high-speed applications, resistive transimpedance amplifiers such as in this part of Lab 4 is used. The next step is to build the circuit. First, inspect the photodiode, which can be one of the types illustrated here. The left-hand side shows a type that looks up, relatively to its through-hole terminals or legs. The right-hand side shows the type that looks sideways, perpendicularly to its legs. They may or may not have a lens built in. It is necessary to identify the 2 terminals, anode and cathode, similarly to the LED. However, the leg length convention for the LED is not used for the photodiodes. Instead, there is usually a band-like marker on the cathode. Shown the figures are the cathode marker for each type. One can use a diode checker on a digital multimeter if in doubt. Care should be taken for the type with a bare sensor area with a thin wire bonded between the anode to the top p-type semiconductor layer. If this wire is broken, the photodiode cannot be used. This circuit is to be used with the voltage amplifier of Part A. Hence, the relative position of the circuits with respect to each other on the breadboard should be taken into consideration. On the left-hand side is the circuit to be built. Notice that pin 6 op-amp output should be coupled to the 1 kΩ input resistor of the voltage amplifier on the right. The op-amp orientations are upside down with respect to each other. This can be changed, if one is concerned with the habit of wiring to the power supplies. Caution should be exercised. Next, when ready. In the follow, the op-amp is placed upside down. The mouse should be hovered to verify the pin number. If one is not comfortable with this configuration, put the op-amp in the upright position, and put wire accordingly with respect to the pins. Insert the op-amp onto the breadboard by gingerly rock back and forth, side to side to align the pins to the holes, and gently push down. Avoid bending the pins. Next, when ready. Connect pin 7 the op-amp to the positive voltage supply, and pin 4 to the negative supply. The power should be off, of course, but make sure the wiring connection from the breadboard to the power rail is correct. Next, when ready, connect non-inverting input pin 3 to ground. If the photodiode is bare and not in a protective housing, hold the photodiode with a tweezer, or a fine tip plier, and insert it onto the breadboard. Be sure the cathode, not the anode, is placed toward the positive voltage supply rail for a wire connection, while the anode is oriented toward pin 2, the inverting terminal of the op-amp, and connected with a wire. The photodiode illustrated is only representative, it is top-looking. The actual one you have might be of a different type, such as side-looking, and appears different. Follow the instruction about the position of cathode and anode next. This is called reverse bias, that is, the cathode voltage is higher than that of the anode. It is opposite to the LED. A photodiode is always used in reverse bias, it should never be forward biased like a LED. If it were forward biased, there would be a large current that would swamp the photocurrent, which is the current of the light signal. To detect a minuscule photocurrent within a torrential forward bias current would be like listening for someone's whisper in a big noisy stadium. In addition, the reverse bias affects a strong internal electric field that increases the photocurrent collection efficiency. Hence, one should check the photodiode polarity and wire it carefully. Here, the positive voltage supply of the op-amp is used for the reverse bias. Every photodiode has a maximum rating of reverse bias voltage, and one should follow the manufacturer's specifications. Next, when ready, connect the 10 kΩ feedback resistor with wires to the op-amp output pin 6 and the inverting input pin 2. Next, when ready, to use it practically, the photodiode transimpedance circuit output should be connected to the input of the voltage amplifier circuit. In other words, 2 stages of amplification are needed. The first stage with the transimpedance amplifier is to convert the photocurrent to a voltage signal. The signal amplitude is usually still relatively low at this stage. The second stage amplifies this voltage signal by a factor from 10 to 100, depending on choice. The combined circuit is an optical receiver, and is now ready for testing. This is an illustration of a built circuit. It is not exactly like the one shown in the diagram previously, and yours does not necessarily look the same. The only thing important is that all the wiring connections should be correct as in the schematic. The exact detailed physical layout on the breadboard is not crucial. The light red enclosure is the transimpedance amplifier. Shown are the photodiode on the left, and the feedback resistor are not on the right. Note that the photodiode is reverse biased, that is, its cathode on the left-hand side is connected to plus 12 volt, and its anode on the right-hand side is connected to pin 2, which is the inverting terminal of the op-amp. The output of the transimpedance amplifier, pin 6, is connected via a red wire to the input terminal of the voltage amplifier that is discussed in Part A, Lab 4, shown here in the bluish enclosure. The input resistor Rin is 1 kΩ, and the 3 feedback resistors can be selected with a blue loop jumper wire for different gains. The optical receiver circuit is connected to the AD2 for measurements. Pin 6 output of the voltage amplifier is connected to a scope channel, shown here as channel 2, but either channel 1 or 2 is fine. In order to test the optical receiver circuit on board, a test LED is put close to the photodiode as shown in the magenta enclosure. The LED is driven by the signal generator of the AD2, which is via a green wire as shown in the figure. This picture shows a different view of the AD2 connection to the circuit. A 6-pin connector is used as the interface between the AD2 and the breadboard. AD2 scope 2 cables are connected to the output of the optical receiver circuit, which is pin 6 of the voltage amplifier op-amp. AD2 signal generator waveGen 1 cables are connected to the test LED driver wires, and also to AD2 scope 1 cables, so that the LED driving signals can be monitored via scope 1, to be compared with the optical receiver output measured by scope channel 2. The circuit is to be tested with the onboard LED transmitter. The test LED was driven with low power and was dim compared with the ambient room light. An enclosure was used to enhance the coupling of the LED and the photodiode. A piece of black cloth was used to further shield the optical receiver from ambient room light. A test was to ensure no detectable change in the current signal when the room light was switched on and off. This shows the measurement screen view of the test. The left-hand side shows the control of the LED square pulse modulation. The square pulse low level is just beneath the LED contact potential, and the high level is enough to yield a photocurrent of 5 microamp, which corresponded to approximately 20 to 25 microwatt optical power. On the right is the display of the scope channels. The LED modulated light was coupled to the optical receiver, whose output was coupled to scope 2, shown as the blue trace. The LED driving signal is shown as the yellow trace. Since the LED square pulse was set on the linear light current curve, its voltage is pretty much linearly proportional to the LED output optical power. Hence, the optical receiver signal has the same square pulse form as the LED driving signal. Given that the transimpedance amplifier resistance and the gain of the voltage amplifier are known, the scope measurement indicates a high-level 5 microamp signal current from the photodiode. The low level is consistent with an independently determined 0.15 to 0.18 microamp dark current. On the bottom is the graph of the signal histograms, which can be used to measure the distinguishability of the signal high and low levels. The transmitter-receiver signals were studied as a function of frequency, which varied from approximately 3 to 260 kHz. As the frequency increases and the pulse shortens, the signal starts to have roll-off, its rising edge and falling off tail come close to each other, resulting in the pulse shape change. The histogram shows that the signal pulses cannot maintain the wide gap between high and low levels as those at low frequencies. The rising edge of each pulse never reaches the full height, and the falling off at the end of each pulse never reaches zero. The signal histograms indicate that the output drops to a half, or 3 dB, around 250 kHz. A relevant question is what limits this bandwidth, the LED, the photodiode, or the op-amps. As the voltage amplifier frequency and impulse responses were tested in Part A, the results indicate that the 741 op-amp, which is designed for audio applications and among the slowest op-amps, alone accounts for this bandwidth. Based on the specifications and known properties of this type of LED and photodiode, their bandwidths are much higher, up to few tens of megahertz. Hence, this optical receiver test is more of a test of the 741 op-amp rather than the optical devices. The key learning idea here is that the op-amp performance figure of merits such as frequency response and bandwidth are not abstract notions in circuit theory, but are based on, and essential to practical applications. This shows the impulse response measurement results. A 200 nanosecond pulse was used to drive the LED. The output optical receiver signal, measured with persistence trace, shows a somewhat complex response with two perceptible time responses. Model fit, as shown in the red trace at the bottom, shows two characteristic times, 1.15 microsecond and 3.5 microsecond. The net equivalent exponential relaxation time is approximately 4 microsecond, corresponding to 250 kHz. This figure is consistent with the frequency response results. Part C is to demonstrate at least two simple tests of the optical receiver. One is a test with a remote control. The other is your choice. You are strongly encouraged to be resourceful and creative, and come up with your own experimentations and demonstrations. Of course, you can choose to do demonstrations similar to those in this video. This note is only to say that you don't have to, and choose whatever that interests you the most. The first test, as mentioned in the introduction, is a simple communication device, the remote control. The remote control light output can be seen with most cameras, unless they have infrared blocking filters. When the remote control light output is applied onto the photodiode, the signal may saturate the receiver, hence, adjust the remote control distance from the photodiode and the scope vertical scale to capture the signals without saturation or overscale. Once a signal is captured, use the scope horizontal, that is time scale, to observe the fine structure of the signal. The signal consists of several bursts of light pulses of different lengths. As the time scale becomes finer, such as 1 millisecond per division, high-frequency modulation can be seen within each burst pulse. This is called carrier modulation. The purpose, like a special pitch whistle a coach might use to catch attention of the coach's team players, this modulation catches the attention of the appliance, knowing that this message with this unique pitch is from the remote control and not the room light or a flashlight, for example. The modulation should be square wave-like, but appeared to roll off here because the optical receiver gain was high and the bandwidth was low, hence the gain was set lower. The carrier wave with 100% modulation depth was captured. Then Fourier transform was applied to show that the modulation frequency is 38 kHz. This is the special pitch that the appliance tunes in, listening only to light pulses with 38 kHz modulation, and tunes out all other interference lights. The following are a few more notes about the remote control. The data here are only for one remote. There are a couple standards for infrared data communications and your remote may have different properties, nevertheless, these are the features you can look for in your measurements. First, try to obtain a whole message associated with a command, such as, turn up the volume. This example shows a burst of signals over a duration of approximately 70 milliseconds. Two most common data coding formats for remotes are non-return to zero and return to zero. More interesting is to look for the initial block known as preamble. It is a signal like a whistle to call for attention. The appliance demodulation and decoding to get the message is based on this preamble. This example shows a 10 millisecond preamble. Another standard may be different. Lastly, this is the feature most interesting to this lab, which is the carrier AM modulation. All bits of the data are amplitude modulated, but it is best to use the long preamble signal to look at the modulation such as shown here. On the 200 microsecond time scale, the AD2 scope data display carrier waveform in details. As shown is the previous video, Fourier transform of the data shows a fundamental carrier frequency of 38 kHz for this remote. Your remote may have a different frequency. If you are not sure how to use the FFT function, you can save the data by exporting the scope trace into a CSV file, such as shown. Then, delete all the non-data rows, as well as the time column and the unused scope channel. Then use the power spectral density calculation app. The Fourier spectrum shows the fundamental frequency at 38 kHz. Do the same to obtain the frequency of your remote control. Now, we can discuss what was done in Part A in the context of this Part C. This explains the use of things like Bode plots. The green line marks the frequency of interest in this case, 38 kHz. This is outside the flat response regions of the curves, known as bandwidths. Consider a low frequency within the bandwidths, the white straight line. The gains marked by the white dots follow the nominal gains of 10 dB, 14 dB, and 20 dB. In comparison, not only the gains at the carrier frequency, marked by the yellow dots, are respectively lower than their lower frequency counterparts, their relative proportions are also different. It appears to be progressively worse, or diminishing return at higher gain. In other words, 20 dB gain is nowhere close to a factor of 10 times relative to 10 dB gain as it should be. The reason would be obvious by looking at the signals. Here are the carrier modulation signals for 10 dB gain, 14 dB gain, and 20 dB gain. A most obvious difference between them is the carrier modulation depth. The 10 dB signal amplitude swings between maximum and zero, which means the modulation depth is roughly 100%, but this becomes only 75% or so at 14 dB, and decreases to just around 35% for 20 dB. It means that at 20 dB gain, the modulated signal doesn't go up and down between a maximum amplitude and zero, but only from the maximum to about 65% or so of the maximum. The magnitude of a modulated signal is not how large its maximum is relative to zero, but only the difference between its maximum and minimum. Thus, higher gain does not necessarily mean proportionately higher signal magnitude if the signal does not go to zero or does not have 100% modulation depth. Thus, in engineering some applications, one must know the frequency response versus gain as shown in the Bode plot, to calculate correctly what to expect and design a system properly. This example once again reiterates the pitfalls of extrapolating any static, steady-state relationship of a linear system into the frequency domain, without knowing the specific properties of the system. Likewise with the frequency domain analysis, we can take a close-up look of the remote control signal with the time domain perspective. The top graph is a fine time scale plot of the signal with 10 dB gain. The bottom graph is the Heaviside step function response done in Part A. Notice the comparable response time. In fact, the response time in the remote control signal should be even slower than that of the signal of Part A, because the optical receiver signal went through two 741 op-amps, and its time response is a convolution of both, which is a tad slower than the single op-amp voltage amplifier response in the bottom graph. Nevertheless, this comparison once again confirms that the limiting factor in time response, and hence, bandwidth, is the speed of the 741 op-amp, which is the slowest of all op-amps, and in fact, is often referred to as a dinosaur op-amp in the electronics hobbyist communities. Here, it is useful to illustrate the implication of time response or slew rate. In Part A, this graph illustrates the roll-off effect that causes an input square wave to yield a triangular or sinusoidal-like output at roughly 38 kHz. The gain was 14 dB, as evidenced in the lower right corner circuit picture inset, hence, the roll-off is slightly worse than that of 10 dB. The bottom line is that these time response and op-amp slew rate measurements of Part A explain the remote control result at the top. Once again, it is worthwhile to remember to never extrapolate a static, steady-state causal relationship to time-dependent quantities. A review of what discussed in Part 1. The op-amp was developed as a solid-state infinite-gain amplifier to substitute the vacuum tube amplifiers that were noisy and unstable for telecommunication applications, which led to the development of negative feedback, which is the circuit of this lab assignment. Harold Black's work in developing negative feedback amplifier was done at the old Bell Labs, the research arm of American Telephone and Telegraph, founded as the Bell Phone Company by Alexander Graham Bell in the late 19th century. It was like a Google of its days. Virtually all the main topics you are learning in circuit theory, and this circuit analysis lab were the results of technological research and development driven by the telecommunication industry of the 20th century. This lab assignment for negative feedback op-amp circuits is a historical legacy of that development. This Part C uses the remote control, a very simplistic communication device, to illustrate the learning subjects of the op-amp, but also as a tribute to its historical telecommunication route. And the optical receiver is also a learning topic to appreciate the present state of the evolution of telecommunications technology, which has come from the first copper wire-based telegraph in early 19th century, to RF wireless in the early 20th century, and now, optical communication technology that engines the Internet since the late 20th century. Next, the optical receiver is used to detect other light signals. This part is a team project. The following are just examples. You and your team are certainly welcome to do similar demonstrations, but are also strongly encouraged to explore and pursue anything of your interests that is relevant to the study. Backscattering is the process that light from a source interacts with objects, which re-radiate the light in a roughly backward direction toward the source. Shining a flashlight, turning on a car headlights are actions that use backscattering. A common technological application involving backscattering is the LiDAR, which is a very broad and comprehensive category that uses lights, usually from lasers, to sense something, be that an object geometrical, polarization properties, or speed such as law enforcement speed LiDAR, or vibration such as Doppler vibrometer, or distributed density, or spectral and chemical signatures. And the backscatter lights can even be of a different nature than the source, such as fluorescence, nonlinearities. Both the most popular and unpopular types involve vehicles. This is an example of a LiDAR that maps surrounding object geometrical distances. This part involves using the optical receiver for a simple laser backscattering demonstration. A red laser pointer was used to shine a spot on a ceiling. The optical receiver was used to detect the backscattered light and to check the scattering process properties. It involves an assumption of a backscattering light distribution, as shown. This distribution was modeled based on the three positions of the photodiode relative to illuminated spot, roughly +25, -25, and 0 degree. The expected backscattered signal current is calculated and plotted as shown. Using the photodiode specifications and the laser specified power, it was found that the detected light signal was within the expected range as shown next. The optical receiver signal, shown as the blue trace, is small because the photodiode sensing area is only a few millimeters squared. A lens was added to collect backscattered light with a larger aperture. The signal is more than 200 times higher with the lens. The laser beam can be scanned to obtain an image of the surveyed objects or area. Although the op-amp here is too slow for any distance-ranging applications, this demonstration illustrates the basic considerations for LiDAR applications. In the follow, the optical receiver was used to detect how LED lightings adjust the light output power. The LED desk lamp has 3 light out settings: low, medium, and high. It was measured with the optical receiver as displayed by the AD2 scope, and in the lower right, recorded with the web camera. Unlike incandescent lighting, which adjusts the light output with the current, LED lighting tends to adjust the output by pulsing the light output at 3 kHz, and varying the duty cycle. Low light is 25% duty cycle, medium is 50%, and high is continuous. The camera recording shows the 3 levels of LED desk lamp output, however it is not as accurate as the optical receiver because of its built-in auto gain control. The LED flashlight also has 3 light out settings: high, medium, and low, but is pulsed at only 250 Hz. This is 10 times this camera frame rate of 25 frames per second, and the aliasing effect can be seen, as the LED light spot on the ceiling shows striation. The same 3 duty cycles can be seen: 25%, 50%, and full. In addition, it also has a 4th setting that is for flashing at very slow rate. A few other LED lights were tested, and it turns out that the scheme of 3 duty cycles are ubiquitous, although the pulsing rates are different. C1 and C2 are sufficient for Part C. You don't have to do anything else unless you are interested and wish to put your work in the team project report. The follow is meant as a preview how this optical receiver in Lab 4 will be used in Lab 5 and Lab 6. You need not to understand the details, it is sufficient to take a look and see how the last 3 lab assignments of the course are related to each other, and all are of the topics of signal processing and analysis. Lab 5 involves building an op-amp oscillator, using the high open loop gain property. The circuit can be used to generate light and sound without any input. By itself, the circuit generates an oscillating voltage, whose frequency can be adjusted with a potentiometer. The optical receiver of Lab 4 can be used to observe the light output behavior. This is a photograph of the 2 circuits. The circuit on the left is the op-amp oscillator that can oscillate 2 rows of LEDs. The output light can be measured with the optical receiver circuit on the right. The human eye can see the LED light, but is neither quantitative nor fast enough to study the light output behavior. Hence, the optical receiver of this lab assignment 4 will come in handy for this task, as will be seen in lab assignment 5. Lab 6 is about signal filtering, such as in communications. Lab 4 demonstration, we observe the signal from a remote control. It is a digital message modulated with a carrier frequency around 38 kHz. The need for the high-frequency carrier, as discussed in Lab 6 Part 1 Step 2, is to allow the signal be distinct from noises and interferences, such as room light, or light from computer, TV, which do not have that particular fingerprint carrier frequency. The photoreceiver on the appliance tunes to that frequency like a radio tunes to a station. It only listens to the messages sent by the remote, and tunes out everything else. Lab 6 circuits are designed to demonstrate that communication technique, that is, amplitude modulation to distinguish the signal from noises and interferences. The circuits consist of band-pass filter from 3 to 10 kHz, and any interferences and noises outside that band are attenuated. The throughput signal is then input into a demodulator to recover the original unmodulated signal. Here it simulates the case of the remote control. A LED will act as the remote control, but with 9 kHz modulation, which matches the band-pass filter in Lab 6. The photoreceiver that was built in Lab 4 will assume the role of the IR receiver on the appliance. 2 sources of light will be the interferences. A flashlight that flashes at 250 Hz, which represents low-frequency interferences, and an actual remote control with a 38 kHz carrier to represent high-frequency interferences. The signal from the photoreceiver will be input into the circuit to test if it can tune in only the LED, and reject the interferences. The LED transmitter is driven by a simulated signal and its light output is coupled to the nearby photodiode. A small enclosure enhances the coupling between the LED and the photodiode. The photoreceiver output shows 100 Hz square pulse that simulates a message, which is modulated at 9.3 kHz square wave. The Fourier spectrum shows the carrier modulation peak. The photoreceiver signal is input into the bandpass demodulator circuit. The flashlight varies its light average output by generating pulses of different duty cycles. The modulation is 250 Hz. As can be seen, the flashlight pulses were filtered out by the bandpass filter of Lab 6. Here, the example shows that this Lab 4 simplistic optical receiver is useful for this demonstration.